Okay, so let's get started. As we were leaving off last class session, we were discussing electron configurations. Now, one of the rules associated with writing out electron configurations and writing out valid orbital diagrams is Hund's rule, which essentially says electrons are placed in empty degenerate orbitals before pairing electrons. So just as a refresher, what do we mean by degenerate orbitals? What does that word tell us? Does it tell us something about orbital energy? What does it tell us?
It's the same.
Yep, same energy, exactly. So if you have a set of orbitals with the same energy, you fill the empty degenerate orbitals first. So for example, let's look at writing out an electron configuration for nitrogen and filling out an orbital diagram. So if we take a look at nitrogen and we go to the periodic table to find nitrogen, what is nitrogen's atomic number? 7. So how many electrons are we dealing with? 7. Okay, again, we're looking for the atomic number, which is the number above the symbol. Okay. Good. So now that we know that we have 7 electrons, nitrogen has an atomic number of 7. We have 7 electrons to work with. Let's write a general orbital energy arrangement. So we have our 1s, our 2s, and our 2p orbitals. Okay, we're going to fill these empty orbitals from the lowest to highest energy. So we're going to start now by filling our 1s with 2 electrons. As we discussed previously, how many electrons can the s subshell accommodate? 2. Okay, we've used up 2 electrons. We're now going to fill our 2s orbital. That takes another 2 electrons. We have a total of 3 electrons remaining. So where do we put the first of these 3 electrons? In the first p orbital, doesn't matter which one, they all have the same energy. Okay, where do we put the second of these 3 electrons? In the second one, in an empty orbital. Yep. And where do we put the last of these 3 electrons? In the third, right? Now, the reason why we fill empty degenerate orbitals first is if you think about what these lines and these arrows are representing, we are representing electrons with these arrows, and electrons are charged particles. And if we place 2 electrons in the same orbital, what we're essentially doing is we are cramming 2 negatively charged particles very, very close together. And as we discussed, like charges, do they attract or repel? Repel. Yeah, this is a repulsive interaction. Electrons repel each other. Okay, so with this example electron configuration in mind, what I'd like you now to do is to write an electron configuration. And we did the orbital diagram. Let's really quickly now summarize this orbital diagram with an abbreviated configuration. So how many electrons do we have in our 1s orbital? 2. So this would be 1s, 2. How many electrons do we have in our 2s orbital? 2. So this would be 1s2, 2s2. And then finally, how many total electrons do we have in the p subshell? 3. Yep. So it's 2p3. Okay. I personally like the orbital diagrams as they're more descriptive on the relative energies of the electrons and whether or not those electrons are paired. We're going to be using orbital diagrams a lot in this next section. So with this overview in mind, what I'd like you to do now is to write an electron configuration for carbon and fill in an orbital diagram for carbon. About that. One moment. There we go. And just to make sure that we're all on the same page, what is carbon's atomic number? Looking at the periodic table, 6. Okay. So I'll be walking around and checking to see how everyone's doing on this, and then we'll come together as a class to discuss. Looks good. Looks good. Yep, looks good. Okay, good. I see a lot of reasonable responses, so I think we're ready to come together to discuss. So first and foremost, we're going to write out our same, as always, orbital energy arrangement. So we have our 1s, our 2s, and our 2p orbitals. What we're next going to do is we are going to fill these orbitals with our 6 electrons. We put our first 2 electrons in our 1s orbital, our second 2 electrons in our 2s orbital, and for the remaining 2 electrons, they go in the 2p orbital, and should they be in the same or different orbitals? Different. Okay. Perfect. And if we were to write a configuration for this, would someone like to volunteer a configuration for carbon? Yes.
1s2,
Yep.
2s2, 2p2.
Yep, exactly right. Perfect. Okay, awesome. Now we're ready to continue on if we don't have any other. Yes.
So the only time you'd ever start pairing them with orbitals, if you had enough, you have to fill them up once, right? And
Yes.
then you start pairing.
Yes, exactly. As long as you're dealing with degenerate orbitals, you fill the empty orbitals first and then you pair. So for example, for oxygen, that's when you start pairing. Yeah. So let's now talk a little bit about valence electrons and their role in chemical bonding. So let me switch colors for this. So atoms typically lose or share their most readily accessible electrons and their highest energy electrons. So in general, the most readily accessible electrons, the electrons that are farthest from the nucleus, are known as the valence electrons. And these are the electrons in the highest energy, principal energy level, the largest N. Now, what does a large N tell us? Are we dealing with a large or small orbital? Are the electrons far away or are they close to the nucleus? Far away, exactly. So the larger your N, the farther the electrons are from the nucleus, the higher energy they are, the more accessible they are for bonding. Now, as a general rule, the Octet Rule states that atoms will gain, lose, or share electrons to reach a noble gas configuration. And a noble gas configuration involves 8 valence electrons. So for example, if we take a look at neon, neon has 8 valence electrons. So it has a configuration of 1s2, 2s2, 2p6. If we count all of our electrons in the largest N shell, how many total electrons do we have in N is equal to 2? 8, because we have 6 plus 2, which is 8. So we have 8 valence electrons. These are our valence electrons. They're the electrons in orbitals with the largest N value, the outermost electrons. Now, in order to help us easily identify our valence electrons, what we like to use are what are called abbreviated electron configurations. These help us identify the valence and core electrons. So in abbreviated electron configurations, what we try to do is to summarize all of our core electrons using a common noble gas. I'll show an example for fluorine just to illustrate this idea. So for example, for fluorine, we're now going to go to the periodic table. And in writing electron configurations, give it one moment. For abbreviated configurations, your first goal is to find the noble gas that is before your element. So what is the noble gas that is before fluorine on the periodic table? Helium. Yep. So we're going to circle helium. So helium is going to summarize all of our core electrons in this case. And then all we have to do is write out the remaining valence electrons for fluorine. Now, before we leave the periodic table, let's take note of a few things. What row is fluorine in? What is the N value of fluorine? 2. So this is N is equal to 2. Okay? And looking at fluorine, if this left-hand set of 2 elements is our S block, are we past the S block? Yes. So we are past the S block. And how many spaces are we into the P block? How many spaces is fluorine into the P block? So let's count. 1, 2, 3, 4, 5. So how many spaces, how many electrons do we have in our P block? 5, exactly. Now, with that information in mind, all we have to do is we've established that helium is our core. We are, and N is equal to 2. We are past the S block, so we write this as 2s, 2. And for our 2p block, we said we are how many electrons into our p block? 5. Does that make sense to everyone? The method of quickly writing abbreviated configurations. Now, how many valence electrons does fluorine have? 7. We have 7 valence electrons. And one nice shortcut that I want you all to remember, fluorine is a 7A element. So our valence electrons are going to be equal to our group number. This is a nice shortcut for identifying valence electrons. So what I'd like you all to do now is I have 2 more examples for you to attempt, and I'd like you to write the abbreviated configurations of oxygen and neon, and I'd like you to identify their valence electrons. Does that make sense to everyone? You have access to the period? Yes.
Since neon is already a noble gas.
Yes, you'd abbreviate it using the preceding noble gas. So you'd abbreviate it using helium. Yep. And this is a copy of the periodic table. Any questions? It's in the earlier pages. Any questions? Yeah, that's good. Yeah, that's good. Okay, I see a lot of reasonable responses. This is review, but I always want to make sure everyone's comfortable with these topics. So for oxygen, would someone like to volunteer an abbreviated configuration for oxygen? Would anyone like to volunteer? Yes.
Helium.
Yep.
2s2, 2p4.
Yep. Helium, 2s2, 2p4. And we know oxygen is a 6A element. So how many valence electrons do we have? 6. Yep. We have 6 valence electrons. Now, if you happen to be really clever, do you notice how we went from 7 valence electrons to 6 valence electrons? So a fast way to write the configuration for oxygen is just take the configuration for fluorine and remove an electron. So we go from 2p5 to 2p4. Okay, would anyone like to volunteer a configuration for neon? Yes.
Helium.
Yep.
2s2.
Yep.
2p6.
Okay, perfect. 2s2, 2p6. And as neon is a noble gas, how many valence electrons do we have? 8. Yep. It's an 8A element. So we have 8 valence electrons. Perfect. Okay. Any questions on configurations? Is everyone comfortable counting valence electrons? Okay. If we don't have any other questions, let's continue on. Just to reiterate, main group elements have valence electrons equal to their group number. Useful shortcut to keep in mind. Okay. So as we discussed, we can write out the configurations for each group in the periodic table. And since the valence electrons are equal to the group number, we notice a repeating pattern for each of the electron configurations, right? The only thing that changes as we move down the periodic table is what? What happened? What changes? N, right? We go from 1s1 to 2s1 to 3s1. If we're in a 1a, in group 1a, do we always have one valence electron? Yes. And the configuration is always the same. The only thing that changes is n, or orbital size. Now, one way that we like to represent and abbreviate the valence electrons is using what is known as a Lewis dot structure. So each dot in a Lewis dot structure represents an electron. So one dot represents one valence electron. So let's just go through really quickly. Lithium is a 1a element in the periodic table. And as a result, if its group number is 1, we have how many valence electrons? 1. Beryllium is a 2a element. So how many valence electrons does it have? 2. So how many dots do we draw? 2. Boron is a 3a. Carbon is a 4a. Nitrogen is a 5a. Oxygen is a 6a. Fluorine is a 7a. And neon is an 8a. Now, is this figure comprehensive for every single main group element in the periodic table? Will it change at all if I replace lithium with, for example, sodium? Whoops, one moment. With, for example, sodium. Is there any difference in the Lewis dot structure of lithium versus sodium, which is also a 1a element? Any difference whatsoever? No. How many dots should I draw for sodium? 1, exactly. Okay, perfect. So to demonstrate this and to make sure we're comfortable writing Lewis dot structures, let's just do 2 of them. I'll start us off with sulfur. So sulfur is a 6a element. So we should have 6 valence electrons. So I'll draw sulfur with 6 dots. Okay. How many dots should I draw around chlorine? 7, exactly. So chlorine is a 7a element. We have 7 electrons. So we draw 7 dots. Okay, perfect. Now that we've established this idea of Lewis dot structures, we can start to generate more sophisticated structures and talk a little bit about covalent bonding. So covalent bonding is of great concern to us organic chemists because it's a primary method in which we form more complex molecules. So covalent bonding is the sharing of electrons between atoms. Again, the reason why atoms share electrons is to attempt to form an octet and to form bonds. The reason why atoms form bonds is that bonds stabilize electrons. Electrons are more stable in a bond than in a lone atom. So in general, we're going to try to form an octet when we form bonds. So, whoops, one moment. Okay, bonding electrons are shared in pairs between atoms, and they are counted as belonging to both atoms in a bond. So what do I mean by that? If we think about a hydrogen-hydrogen single bond, we can either abbreviate with a line or with a pair of dots. We have 2 electrons shared in a bond between our hydrogen atoms. And if we look at each hydrogen atom individually, let's define how many electrons belong to each hydrogen atom. So looking at this hydrogen atom on the left, how many electrons does that hydrogen atom have to its name? 2. Has 2 electrons because it has 2 electrons from this bond. What about the hydrogen atom on the right? How many electrons does it have to its name? 2. Bonding electrons are counted as belonging to both atoms in a bond. Okay, perfect. So both of these hydrogen atoms have a quote-unquote helium-like configuration, and they're stabilized as a result of this. Now, lone pair electrons or non-bonding electrons are electrons that are not shared between atoms. Lone pair electrons are counted as belonging only to the atom containing the lone pair. So let's use an example of water, and let's take a look at water. I'll draw out a valid Lewis structure for water really quickly so we can begin to discuss bonding pairs and lone pairs. Okay, so now that we've drawn out water, my question to all of you is, looking at this hydrogen on the left, how many electrons are belonging to this hydrogen on the left? 2. Has 2 electrons from this bond. So this hydrogen has 2 electrons to its name. Looking at the oxygen atom, how many electrons does this central oxygen atom have to its name? 8. It has 4 electrons from our lone pairs, plus 4 electrons from the chemical bonds, for 8 electrons total. The hydrogen on the right has 2 electrons to its name. Okay, perfect. So we know how to count electrons and verify that the octet rule is in fact followed. Okay, perfect. So let's talk a little bit about how we represent different types of bonds and how we count electrons for different types of bonds. So we typically write bonds as lines between each atom. Each line represents 1 bond or 2 shared electrons. If we have 1 pair of bonding electrons, we're dealing with a single bond. For example, a fluorine-fluorine single bond involves sharing 2 electrons. So this line represents 2 electrons. Now, of course, we can share more than just 1 pair of electrons and form multiple bonds. So for example, if we have 2 pairs of bonding electrons, we have a double bond. This is often found in oxygen. It's a marquee example of that. So each oxygen atom has 8 electrons to its name, and shared between these 2 oxygen atoms are how many electrons? How many electrons have we shared? 4. 2 times 2 gives us 4 electrons shared. Perfect. And finally, we can share 3 pairs of bonding electrons and form what's known as a triple bond. So in the case of nitrogen, nitrogen in its elemental form likes to generate a triple bond. It is often a byproduct or a side product of organic reactions, and it's a nice thermodynamic sink. And as we've discussed, how many electrons are shared between these nitrogen atoms? 6. Yeah. Okay, perfect. So with this run through of chemical bonding and what each of these bonding conventions represent, we're now going to start to generate what are known as Lewis structures. We're going to try to draw plausible arrangements of bonds and atoms for a given chemical formula. So we're trying to draw plausible, stable structures for a given chemical formula. As a general rule, most stable structures will fulfill the octet rule and they will minimize formal charges. We'll talk more about formal charges in a moment. So I like to use procedural methods whenever I can, when I'm dealing with solving problems. So let's go through the general procedure for drawing Lewis structures, and let's talk a little bit about why I have each of these steps. So first and foremost, you're going to count the total number of valence electrons for all atoms. Remember, you can use the trick where the group number is equal to the valence electrons. Now, if the species is a cation, do we have more or less electrons than usual? Less. So we have to subtract electrons equal to the charge. If the species is an anion, do we have more or less electrons than usual? More. So we have to add electrons equal to the charge. your next goal is to determine the central atom. Now, of course, there can be more than one central atom, but in general, the central atom is never hydrogen, and it's the least electronegative atom. We'll have an electronegativity table on the next page. Now, in general, you want to arrange atoms symmetrically around the central atoms, and for n equals 1 and n equals 2, so the first two rows of elements in the periodic table, you can only have a maximum of 4 atoms around the central atom. Would anyone like to provide insight as to why that rule exists? What happened? Yes.
Generally, if you have more than 4 single bonds, you'll dissipate the octet.
And what happens after the second row? What orbital becomes available?
D.
D, yeah. So for the first and second row, you don't have an empty d orbital. And we'll see that when we talk about expanded octets. Okay, from here, what you're going to do is you're going to form a single bond, 2 electrons, 1 line, between the central atom and each surrounding atom. The reason why I like this procedural method is it avoids common errors associated with Lewis structures. Once you've formed a single bond, you're going to subtract 2 electrons from the total for each bond that you formed. Next, and only after you've formed your bonds, you're going to place electron pairs around the outer atoms. And you're going to prioritize the most electronegative atoms first. That makes sense, right? Electronegative atoms want electron density, so you put your lone pairs on the electronegative atoms first. Once you've completed the octet of all of your atoms, or if you run out of electrons, then you'll move on to the next step. If for some reason you've run out of electrons and the octet rule cannot be fulfilled, you're going to convert lone pair electrons into a double bond or triple bond until the octet is fulfilled. This is a common mistake I see a lot of students make. Please only use a double or triple bond if it is needed. Do not start by drawing double and triple bonds. Draw them only at the end if you run out of electrons. Now, I mentioned the word electronegativity. So let's talk a little bit about electronegativity, and let's show the electronegativity table. So what is electronegativity? Electronegativity is a measure, quite simply, of how readily an atom of an element attracts electron density in a chemical bond. Now, in general, as you move up the periodic table and as you move to the right on the periodic table, you have more protons in your nucleus relative to the outermost orbital. Your electronegativity increases. So your electronegativity increases as you move up the periodic table. You have small n, your electrons are closer to the nucleus. And as you move to the right on the periodic table, where you have a greater number of protons, or you could say there's a large effective nuclear charge. Now, the electronegative elements are primarily our nonmetals on the upper right of the periodic table. Now, to help everyone out so that way you don't have to consult the table every single time, I generated a common hierarchy for electronegativity of all the common elements that you'll see in organic chemistry. So, of course, fluorine is the king of electronegativity. Let's show this in context. So fluorine is the absolute king of electronegativity, has an electronegativity value of 4.0. Of course, followed by oxygen and nitrogen. Now, a few things that I'd like you to see from this electronegativity hierarchy. Carbon and hydrogen are very, very close in electronegativity, such that a carbon-hydrogen bond isn't very polarized. The other thing I'd like you to note, if we compare nitrogen and phosphorus, do we notice a pretty dramatic drop in electronegativity? Yes. The phosphorus-hydrogen bond is polarized in an entirely different direction. Same with looking at a carbon-phosphorus. Comparing carbon and phosphorus, what's more electronegative? Carbon. This will be important later on when we talk about Wittig reactions and other reactions involving carbon-phosphorus bonds. Does electronegativity make sense? Have you seen this type of table before? Okay, we'll be using this in a moment. Okay. So let's do some practice on Lewis structures. I'll start us off with the first one, and then you'll do 2 examples. So CCl4, carbon tetrachloride. First things first, I'm going to count my total number of valence electrons. So carbon is a 4A, so it contributes 4 electrons. Chlorine contributes 7 electrons, and we have 4 chlorine atoms. That gives us 32 electrons total to work with. Now, looking at the electronegativities, carbon is the least electronegative element, so I'm going to put carbon in my center, and I'm going to surround it with my 4 chlorines. Next, following my rules, I'm going to form 1 bond each. Okay, so from this, I have used up 2, 4, 6, 8 electrons, and I now have 24 electrons to work with. Next, I'm going to place lone pairs on my chlorines to complete the octet. So how many lone pairs do each of these chlorines need? Well, three sets of lone pairs, 6 electrons, however you want to look at it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And with that, we are out of electrons. This structure obeys the octet rule. We've used all of our electrons, so this is a complete Lewis structure. Okay, what I'd like you now to do is to draw valid Lewis structures for the next 2 compounds, ammonia and methanol. Good, good, good. Any questions? Looks good. Any questions? Everyone's really fast at this. That's good. That's good. So let's talk a little bit about ammonia. And let's try and draw a valid Lewis structure for ammonia. So nitrogen contributes 5 electrons. Hydrogen contributes 1 electron. And of course, we have 3 hydrogens. So that gives us a total of 8 electrons to work with. What is our central atom going to be? What's the least electronegative non-hydrogen atom? Nitrogen. Yep. So we're going to put nitrogen in the center, and we're going to surround it with our 3 hydrogens. Next, we're going to form 1 bond each. We've used up 2, 4, 6 electrons. So we only have 2 electrons left. Okay. Nitrogen does not have a complete octet. So how many additional electrons does nitrogen need? 2. So we're going to place a lone pair on nitrogen. And with that, we are out of electrons, and the octet rule is fulfilled for all atoms. Yes?
So when we're doing these Lewis structures, does it matter the angle of that we're drawing?
Yes. So I'm drawing these in order to respect their geometry. So this is just a habit that I want you to get into in drawing all of your molecules respective of the correct molecular geometry. And we'll talk about that in a moment. Okay, so let's, whoops, sorry about that. One moment. So let's now talk about methanol, or CH3OH, methyl alcohol, whatever you want to call it. Carbon contributes 4 electrons. Hydrogen contributes 1 electron, and how many hydrogens do we have? 4. Yep. Okay, oxygen contributes 6 electrons. So in total, we have 8 plus 6. So we have 14 electrons to work with. Now, in terms of our central atoms, what's our first central atom going to be? What's our first? Carbon, yep. And a beautiful thing about this formula is actually known as a condensed formula. It tells you the exact ordering and arrangement of your atoms. So it tells us we have a carbon with 3 hydrogens attached, and then an oxygen with a hydrogen attached. So I'm going to make carbon my first central atom, and I'm going to surround it with 3 hydrogens. What's our second central atom going to be? Oxygen, exactly. And I'm going to surround it with our remaining hydrogen. Does everyone notice how the way that the formula is written directly corresponds to the way that I wrote my atoms in the Lewis structure? Reading condensed formulas makes this process so much faster. Okay, next we're going to form 1 bond each. 1, 2, 3, 4, 5. So we formed 5 bonds. How many electrons did we use? 10. Yep. So we have 4 electrons remaining. Are there any atoms that are not particularly happy? Are there any atoms with an incomplete octet? Oxygen. Wait, yep, oxygen. And how many electrons does oxygen need? 4. Yep, so we'll add 2 lone pairs. 1, 2, 3, 4. Any questions on these Lewis structures? Okay. We'll start to increase the complexity of our Lewis structures as we continue on, but I just want to make sure everyone's on the same page. So these are a few slightly more complex structures. I'll start us off. This is a case where we have to form double or triple bonds. In this case, we're dealing with our good old friend formaldehyde. Carbon contributes 4 electrons to its name. Hydrogen, 1 electron, and we have 2 hydrogens. And oxygen contributes 6 electrons. This gives us a total of 12 electrons to work with. What's our central atom going to be? Carbon. Yep. We're going to put carbon in the center. We're going to surround it with an oxygen and 2 hydrogens. And then we're going to form 1 bond each. We have formed a total of 3 bonds. Ergo, we've used up 6 electrons. We have 6 electrons left. Now, looking at oxygen, does oxygen have a complete octet? No. So we need to give it how many additional electrons? 6. So we'll add 2, 4, 6. Okay? We are out of electrons. Is the octet rule satisfied for all of our atoms? No. Carbon only has 6 electrons to its name. So we are going to take one of these lone pairs and we're going to move it down to form a double bond. So let's draw our new revised structure with our double bond. Perfect. Now this structure follows the octet rule and is a correct and valid Lewis structure. So with that in mind, I'd like you to attempt these next 2 example, or this next single example of hydrogen cyanide. Yeah, looks good. Yeah, looks good. Any questions? So far, so good.
Okay.
Any questions? Okay. Yep, looks good. So let's talk a little bit about this problem and let's talk about how to handle this system. So HCN, hydrogen contributes 1 electron, carbon contributes 4 electrons, and nitrogen contributes 5 electrons. That gives us 10 electrons total to work with. What is our central atom going to be? Carbon. Yep. Okay, and we're going to surround it with hydrogen and nitrogen. as our next order of business, we're going to form one bond each. We have used up how many electrons? 4. Yep. So now we have 6 electrons remaining. With these 6 remaining electrons, which outermost atom has an incomplete octet? Is nitrogen happy with this arrangement? No. How many electrons does it need? 6. So we're going to place our lone pairs on nitrogen. We're going to use up our 6 electrons. And now nitrogen certainly is happy, but does carbon have a complete octet? No. So let's move one of our lone pairs down. Is carbon happy with just one lone pair being moved down? Is it just happy with a double bond? No, it needs a triple bond. Okay, once we've formed a triple bond, we end up with the following revised structure, which satisfies the octet rule on all atoms. And if you're curious why we have the hydrogen bonded to carbon instead of nitrogen, that has to do with the idea of formal charges, which we'll discuss later on in today's lecture. Any questions before we move on from, yes?
Would this to be a linear structure?
Yes, it would. Yeah, that's why I drew it like a dart as a respective of the linear geometry. Exactly right. Mm-hmm. Okay, let's try to draw Lewis structures for slightly more difficult chemical formulas. And in this case, I'm starting to introduce you all to the idea of condensed formulas. Now, what this means is if you read the chemical formula from left to right, it gives you a hint on the connectivity of the atoms involved. So first and foremost, carbon contributes 4 electrons, and we have 1, 2, 3 carbon atoms. So 4 electrons times 3. Hydrogen contributes 1 electron, and we have 6 hydrogens. Oxygen contributes 6 electrons to its name. Okay, so we have 12 plus 12. We have 24 electrons to work with. Now, following our guideline from the formula. So our formula is CH3COCH3. So what's our first structural feature? Exactly right. Carbon bonded to 3 hydrogens. Okay, what's our next structural feature? Carbon, yep. And what is bonded to that carbon? Oxygen, yep. Okay, and then what is also bonded to that carbon? Yep, so another carbon with 3 hydrogens. Okay, so just as a side note, this CO noted in the chemical formula is known as a functional group, which we'll discuss in more detail later in this chapter. And as we'll see, it corresponds to a unique arrangement of bonds. So this is our skeleton. So from our skeleton, we formed 1 bond each, right? So all we have to do is count the number of bonds that we formed and then move from there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we formed 9 bonds and we've used up 18 electrons. So that means we have 6 electrons remaining. Okay. From this skeleton now, are there atoms with an incomplete octet? Oxygen. And how many electrons does oxygen need? 6. Yep. 2, 4, 6. Okay, wonderful. We are out of electrons. Are there any atoms with an incomplete octet? Carbon. Okay, so what should we do? Yep, form a double bond. So we're going to erase one of these lone pairs, and we are going to form a double bond. Perfect. Now we have a structure that follows the octet rule. And in this case, this carbon in the middle should be trigonal planar, but I was just drawing the skeleton out. Does anyone recognize this molecule? Principal component of nail polish remover, also known as acetone. Okay, let's try drawing a few more complicated Lewis structures. This time, I want you to draw a valid Lewis structure for what is known as acetic acid. Again, I encourage you to use the skeletal method for drawing out this Lewis structure, or you can do the Longham method, whatever you prefer. So, one question would be, is that structure minimizing the formal charge? The structure is almost perfect. I was thinking about where to put the hydrogen. Any questions? Any questions? Any questions? Okay. Any questions? All would attach to one of the oxygens, and the reason being, think of hydrogen a little bit like a lone pair, and if you're trying to minimize formal charges, you'll find that in all the arrangements, the arrangement with hydrogen on the oxygen is the lower formal charge structure. Yep, looks good. Yes. Mm-hmm. Yep. Mm-hmm. Yep, exactly right. Mm-hmm. So I see a lot of good progress. So we're going to discuss this just so that way we can stay on track. So for carbon, it contributes 4 electrons, and we have 2 carbons. Hydrogen contributes 1 electron, and we have 4 hydrogens. Oxygen contributes 6 electrons, and we have 2 oxygens. So again, conveniently enough, we have 12 plus 12, or 24 electrons to work with. We'll talk about why that is later on in this class. So following our skeleton, if our skeleton is CH3CO2H, so this is also another functional group, a common structural motif known as a carboxylic acid. Don't worry about that for now. Now, looking at this formula, what's our first structural motif? Yep, so a carbon with 3 hydrogens attached, or a methyl group. And that carbon is attached to what? Another carbon, yep. Now, we know that this carbon is attached to 2 oxygens, and there was a lot of contention over where do we put that hydrogen. I will tell you that it's attached to one of these oxygens, and we're going to use formal charge rules that we'll discuss in about 2 minutes to justify that. So the hydrogen in general can be thought of similar to a lone pair for the purposes of electron counting, but in general, hydrogens are preferred to be attached to more electronegative atoms in Lewis structures. Okay, with this skeleton, we formed 1, 2, 3, 4, 5, 6, 7 bonds. We've used up a total of 14 electrons. We have 10 electrons remaining. Let's now switch to the lone pair color. And do we have any atoms with an incomplete octet? Oxygen, both of them. So this top oxygen needs how many electrons? 6. Okay. 2, 4, 6. This bottom oxygen needs how many? 4. 2, 4. Okay, perfect. We have 0 electrons remaining. Now, are there any atoms with an incomplete octet? Carbon. Okay, so we have to move a lone pair down. And again, there was a question of which lone pair do we move down? Well, following formal charge rules in general, you move down a lone pair from the atom with the most lone pairs. So in this case, which? Oh, no, the top. Yeah, exactly. If you happen to move the bottom oxygen's lone pair down, you'd end up with a positive and negative formal charge, and that's not favorable. We'll talk about formal charges in a moment. So this is a complete Lewis structure for acetic acid. And don't worry, we're still developing our skills to assess what a good Lewis structure is and what a preferred Lewis structure is. So no worries if you formed a double bond down here. We're still fleshing out the rules. Any questions before we move on? Is everyone okay with the pacing so far? Okay. Don't be shy to raise your hand and ask questions. So let's talk about a few common anions. And all of these structures are strategically chosen as these are intermediates that we'd encounter throughout this class. So I'll do the first one. This is BH4 or Borel Hydride. Now, if we have an anion at play, we add electrons equal to the charge. So boron is contributing 3 electrons. These hydrogens are contributing 1 electron, and we have 4 of them. Since we have a -1 charge, do we add or subtract an electron? Add, exactly. So we have 8 electrons to work with. What is our central atom going to be? Boron, yep. So we're going to take boron, surround it with our 4 hydrogens, and form 1 bond each. How many electrons have we used up in the process? 8. Okay. The only thing special about this structure is the fact it is charged. So we have to indicate the charge in brackets. And if you're curious which atom has that negative charge, it's the boron atom. Any questions on tackling anions? I'm going to let you loose now, and I'm going to have you draw valid Lewis structures for the following 2 anions. So in general, we prefer to place excess lone pairs on the more electronegative atoms. Yeah, so instead of having carbon with a lone pair, you move the hydrogen one and put a second lone pair on. So there's 2. Yes, exactly. Yep. That stems to the fact you don't really want to put electrons in the more electronegative atoms. Any questions? Yep. Yes, it's better. Any questions? It's good. Any questions? Okay. And so looking at the structure that you have, the skeleton is correct. However, in counting your electrons, the structure drawn has 4 few electrons. Or, oh, sorry, let me rephrase. So the structure you have drawn doesn't follow the octet rule for carbon. So how did you get those?
Oh, I see.
How did you get those double bonds?
Double bonds?
You probably got them from the lone pairs. Instead of having the double
There you
bonds,
go.
just keep the lone pairs. Yep, exactly right. Mm-hmm. Any questions? Looks good so far. Yes.
So in this situation, we have the oxygen left.
Yep.
Can you hear oxygen?
Hydrogen only forms 1 bond, and does carbon have a complete octet? Yep. If you're curious, the second example is a derivative of methanol, an example that we've already drawn in this class. It's just methanol with 1 less hydrogen. So I saw a lot of reasonable answers for this first prompt. So let's discuss. This is dimethylamine anion. So let's talk a little bit about this. Carbon has 4 electrons to its name. and we have 2 carbons. Hydrogen contributes 1 electron, and we have 6 hydrogens, and nitrogen contributes 5 electrons. This species has a -1 charge, so do we add or subtract 1? Add, yep. Okay, so we have 8 plus 6 plus 6, so we have 20 electrons to work with. Following our condensed structure, what's our first motif? CH3, or a methyl group. Okay, this carbon is attached to what atom? Nitrogen. And what is attached to the nitrogen? Yep, another CH3, or another carbon with 3 hydrogens attached. Okay, from this we've used up 2, 4, 6, 8, 10, 12, 14, 16 electrons. We now have 4 electrons remaining. Where do we place our last 4 electrons? Are there any? Yep, exactly right. We place it on nitrogen. Okay, sorry about that. Yep, 1, 2, 3, 4. Nitrogen has a complete octet, and this entire species is charged, has a -1 charge. Would anyone like to take a guess? What atom has the negative charge? Nitrogen. Yep, this nitrogen has a formal charge of -1. Okay, so for the next example, CH3O-, let's talk a little bit about this. This is a derivative of methyl alcohol. So carbon has 4 electrons, hydrogen 1 electron, and we have 3 hydrogens, and oxygen is 6 electrons. We also have a -1 charge, so we take our 13 electrons and add 1 to it. So we have 14 electrons to work with. Now, following our condensed formula, we're going to write out a CH3 functional group, and then attached to the carbon is an oxygen. How many electrons have we used up so far? 8. Okay, perfect. So we have 6 electrons remaining. And what we're going to do with those 6 electrons, what atom has an incomplete octet? Oxygen. Yep. 2, 4, 6. Okay, this whole structure is charged. And where do we place our negative charge? Oxygen. Yep. If you use your formal charge rules, that oxygen in fact has a negative charge. Perfect. Let's do some more practice on drawing Lewis structures. Sorry, let me just stay on this portion. Just to make sure, are there any questions before we continue on? Yes. Both are fine. The reason why I'm writing the charge inside is to show the fact that the total charge of the molecule is the sum of the charge of each atom in the molecule. Yep. Hmm? Yes.
Well, does it say just only one of the lone pairs are the ones that have the charge?
In most cases, yes, but we'll talk about the rules for calculating formal charges in a moment. So the way this is calculated and the way that we assign these negative charges to each atom or positive charges are based on the formal charge formula. So we'll talk about that in a moment. So in order to ensure we're well-rounded in our practice, let's now deal with some cation Lewis structures. So for cations, they have less electrons than normal, so we subtract electrons equal to the charge. So I'll start us off with the first one. In this case, we have CH3, CH2, NH3+. Okay, so looking at carbon, carbon has 4 electrons to its name, and we have 2 carbons. Hydrogen has 1 electron to its name, and we have 8 hydrogens. For nitrogen, it contributes 5 electrons. So we take our total, in this case, which is 21, and we subtract our charge of +1. So we have 21 minus 1. That gives us 20 electrons to work with. Does that make sense to everyone? Make sure you're counting electrons correctly, or you will not get the correct structure. Now, following my skeletal arrangement, what's the first structural motif we will see? Yep, so looking at the formula, CH3CH2, NH3. I'm going to write a carbon with 3 hydrogens attached. Then attached to that carbon is another carbon with how many hydrogens? 2. Yep. And then attached to that carbon is what? Nitrogen. And that nitrogen has 3 hydrogens attached. Okay, we formed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds. Let me check really quickly. 8, 16, 21, 3, 6, 8. Yes, that's fine. 8, that's 8. Yes, that's fine. Let me count one more time. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yep, that's correct. We formed 10 bonds. We've used up all 20 of our electrons. Does this structure follow the octet rule? Yes. If you're curious, the positive charge is centered on nitrogen in this case. And this entire structure should be put in brackets, and you should put a positive charge. Everyone comfortable doing a few examples on your own? Okay, so I'm going to let you loose on these next 2 examples. The first one is easy. The second one is slightly tricky. Okay. Yep. Yep. The formal charge of total of all that. Any questions? That's good. Yeah. Yeah. And then the second structure, does it follow the octet rule? So try to draw a structure that follows the octet. Yep, looks good. Everyone's quite fast at these. So H3O plus is a bit of a freebie, but always want to get everyone in the habit of drawing these structures. So for H3O plus, for hydrogen, we have 1 electron and we have 3 hydrogens to work with. For oxygen, we have 6 electrons. So we have 9 electrons. And since we have a charge of +1, what do we do? Subtract 1. Yep. So we have 8 electrons to work with. We put oxygen in the center. We surround it with 3 hydrogens, and we form 1 bond each. How many electrons are we left with? 2. Yep. So we have 2 electrons to work with. And where do we place those 2 electrons? What? Yep. We need to fulfill the octet of oxygen. And as we see, oxygen now has a complete octet. We put our entire structure in brackets with the charge, and in this case, the oxygen has a positive charge. Okay, the second example is a little bit tricky, but it's a common intermediate that you see in some reaction mechanisms. All of these structures are chosen deliberately to prepare you for later portions of this class. So for carbon, we have 4 electrons to work with, and we have 2 carbons. For hydrogen, we have 3 electrons. Oh, let me write this out more clearly. We have 1 electron and 3 hydrogens. And for oxygen, we have 6 electrons. Looking at our total, we have 17 electrons. What do we do with our positive charge? Subtract. Yeah. 17 electrons minus 1, we have 16 electrons to work with. What's our first structural motif? Yep, exactly. Okay, and attached to that carbon is another carbon. Yep, and attached to that carbon is an oxygen. Okay, we have formed a total of 1, 2, 3, 4, 5 bonds. So how many electrons have we used? 10. So we have 6 electrons remaining. Let's now switch to my lone pair color. And what outermost atom, yep, exactly. Oxygen's electronegative, it's an outermost atom. And how many electrons does it need? 6. 2, 4, 6. Wonderful. Is that carbon in the middle very happy with this arrangement? No. So if we move one lone pair down, so let's draw it for everyone. So if we move a lone pair down to form a double bond, is that carbon, does it have a complete octet? No. So we need to move another lone pair down. Okay, perfect. Now this structure follows the octet rule. We put our positive charge, and this oxygen itself is positively charged. In general, any oxygen with 3 bonds and 1 lone pair will have a charge of +1. Any questions on these more complicated Lewis structures before we continue? Don't be shy to ask questions. Everyone good?
The triple bond being
Yes.
here.
Yes, exactly right. Mhm. Now, let's talk a little bit about formal charges. And let's talk a little bit about rules for assessing valid Lewis structures. So formal charges, favorable Lewis structures or good Lewis structures have small formal charge values, have few atoms with a non-zero formal charge. And if you have to have formal charges in your molecule, in general, you're going to put the negative formal charges on the more electronegative atoms and the positive formal charges on the less electronegative atoms. That makes sense, right? Electronegative elements like electron density. They like excess electrons. They like negative charges. Now, the formula for formal charge is the group number of an atom minus the number of bonds combined with the number of lone pair electrons. Does everyone notice the distinction in language? You're counting bonds for this part and lone pair electrons, the dots, for the second part. Now, as a general rule of thumb, the total charge of a molecule is equal to the total formal charge of all atoms. So if you add up all of your individual formal charges, you should get the total charge of your molecule. Now, let's look at an innocuous structure, and let's talk a little bit about the fact that this structure does have atoms with formal charge, but it is neutral. This is the stereotypical formula or the skeleton of an amino acid. So let's try using the skeletal method. Let's try to get away from just counting electrons. Let's try to use this skeleton to generate a cogent Lewis structure. So what's our first functional motif? NH3, okay? Okay, and that NH3 is attached to what functional motif? Yep, a carbon with 2 hydrogens attached. And that carbon is attached to what? CO2. So a carbon with 2 oxygens attached. Okay, perfect. Now, just thinking about what does this molecule need for a complete octet? How many bonds does this carbon need? 4. So looking at this, we currently have 3 bonds. So do we need a double bond? Yes. Okay, perfect. Now let's add our lone pairs. Are each of these oxygens happy with this current situation? No. So in order to have an octet on this top oxygen, how many lone pairs do we need? 2, because we need a total of 8 electrons. We have 4, we need 4 more. This bottom oxygen, how many electrons does it need? 6. It has 2. What plus 2 gives us 8? 6. 2, 4, 6. Okay. Now we're ready to start calculating formal charges. So let's start with nitrogen. Does everyone get the process between writing out a Lewis structure using the skeletal method? The trick is you write out your baseline skeleton and then you form the bonds needed to complete the octet for all atoms in your structure. It's a nice shortcut. Yes?
Does it matter which oxygen you put the double bond on, or is it the
It
same?
does not matter. They're functionally equivalent, but that's a good question. Any other questions on this method? So let's now talk about formal charges. Let's start with the nitrogen. So what is nitrogen's group number? What is nitrogen's group number from the periodic table? 5. Yep. So nitrogen is a group 5 element. How many bonds are present on that nitrogen? 4. Yep. Are there any lone pair electrons, any dots on that nitrogen? No. So 5 minus 4 gives us a formal charge of +1. So we put a +1 or just a plus next to nitrogen. You technically don't have to put the 1. I'm just showing it so that way you can see. Formal charge of +1, we put a plus. Okay, let's do carbon. Let's do this middle carbon. What is carbon's group number? 4. Yep. How many bonds does this middle carbon form? 4. Yep. Does carbon have any lone pairs, any dots on? No. So carbon has a formal charge of 0. You do not have to write a formal charge of 0 on every single atom. It's redundant. Okay. Let's look at this top oxygen. So the oxygen, I'm going to abbreviate this as OT. T for top. Okay. Now, looking at this, what is oxygen's group number? 6. Okay. How many bonds are attached to this oxygen? 2. Okay. And how many lone pair electrons does it have? 4. Yep. So we have a formal charge of 0. Okay. Now, implicitly, what do we know about this structure? Is there a negative formal charge somewhere in this molecule? Yes, and the way that we know, we have a positive formal charge and we have a neutral molecule, right? So there must be a corresponding negative formal charge somewhere in this molecule. So let's look at the bottom oxygen, What is, oh, whoops, sorry, one moment. There we go. Okay, so oxygen's group number again is 6. How many bonds does this bottom oxygen form? 1. And then how many lone pair electrons are attached to that oxygen? 6. So that gives us a formal charge of -1. So we put a negative symbol next to that oxygen on the bottom. Does that make sense how to calculate formal charges? Okay, let me zoom in just a little bit more. Okay, perfect. So what I want you to do now is to draw out the following Lewis structure and assign formal charges. This may look like an innocuous formula, but it's a good test. Any questions? Perfect. And then you can put the formal charges in each of the corresponding items. Otherwise, it's 100% correct. Any questions? Make sure to, so when you're drawing from the skeleton, make sure to form double and triple bonds only as a last resort. Right. For that one, try using the method that we use for the simpler Lewis structures. So looking at that, so it's the reason is it's almost correct. I would just count your total number of electrons and see if the structure has the same total number of electrons. Mm-hmm. Yeah, looks good. Any questions? Oh, I would check if the total number of electrons matches between those two structures. So here we have, I think it has 2 or less electrons. Sure. So let's talk a little bit about this example. I really want you to feel free to always count your electrons in case that you see a structure and it doesn't look quite right. You can also identify if your structure has a major error because the formal charges will not add up to the correct total. So, for example, for ozone, this is pretty easy to calculate. We have 6 times 3, or 18 electrons to work with. So we have 3 oxygen atoms. It does not matter what the central atom is. It's going to be oxygen, of course. So we have our 3 oxygen atoms, and we're going to form 1 bond each. So we have 14 electrons remaining. Let's now switch to our lone pair method. So looking at these outer oxygens first, how many electrons do each of those oxygens need? 6, yeah, right? They have 2, they need 8, so they need 6 more. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, we have 2 electrons remaining. Where do our last 2 electrons go? Is there an oxygen with an incomplete octet? Yeah, the one in the middle, right? Okay, perfect. Now, from here, looking at this structure, is the octet rule fulfilled for all of our atoms? No. This middle oxygen needs how many more electrons? 2. We don't have any more electrons to give. We used up our last 2. So what we have to do is take one of these lone pairs and form a double bond. Exactly. Okay, perfect. Now the octet rule is fulfilled for every single atom in this structure. If for some reason you omitted these 2 electrons and you formed another double bond, you would be able to notice your structure had an error by virtue of the fact that the formal charges will not cancel properly. So let's show what I mean by that. So let's calculate the formal charge of the oxygen on the left. So we're looking at this one right here. So what's the group number of oxygen? 6. Yep. And how many bonds does this oxygen have? 1. Yep. And then how many lone pairs does it have? 6. Okay, so that gives us a formal charge of -1. Did we just do this calculation in the earlier example? Yes. Does everyone notice how an oxygen with 1 bond and 3 lone pairs always has a formal charge of -1? We are starting to develop this idea of bonding motifs. So let's put the minus symbol next to this oxygen. Let's look at the oxygen in the middle. So the oxygen in the middle, the group number is still 6. Oxygen is still oxygen. How many bonds have we formed? 3, yep. And how many lone pair electrons do we have? 2. That gives us a formal charge of +1. In general, an oxygen with 3 bonds and 1 lone pair will have a formal charge of +1. Okay, finally, let's look at the oxygen on the right. Has a group number of 6. How many bonds does this oxygen have? 2. And how many lone pair electrons does this oxygen have? 4. Yep. Okay, we have a formal charge of 0. Does everyone notice how an oxygen with 2 bonds and 2 lone pairs has a formal charge of 0? The reason why I like this example is it showcases all of the common bonding motifs and formal charges for oxygen atoms. Does it really matter the fact that this oxygen atom is in ozone, or does it only matter the bonds and the lone pairs around it? Yeah, if I erased this portion and we're just looking at this oxygen isolated, the formal charge calculation stays the same. So it really would be useful for you to get in the habit of calculating the formal charges for common bonding motifs and just being familiar with them. So that way you don't have to spend the time using this formula every single time. So in the last few minutes, let's continue on and let's talk a little bit about how to draw Lewis structures quickly. This is how most students in organic chemistry are actually going to be drawing their Lewis structures, and it involves utilizing bonding preferences and formal charge rules. So have any of your instructors ever showed you this table before? It essentially shows that as you move to the right in the periodic table, the number of bonds and the number of lone pairs change. So for hydrogen, hydrogen likes to form one bond with 0 lone pairs. So our number of bonds increases to 4 for carbon. Carbon likes to form 4 bonds. And then past carbon, nitrogen, oxygen, and fluorine like to form successively 1 less bond and instead like to have lone pairs. This has to do with the formal charge calculation, but this is a nice little mnemonic to remember for common bonding preferences. Carbon likes to form how many bonds? 4. Nitrogen likes to form how many bonds? 3. And how many lone pairs does nitrogen like to have? 1. Yep. It's best thought of as like the rule of 4. Now, from this common bonding preference, we can make a series of building blocks for neutral elements, right? So hydrogen is always going to want to form 1 bond, right? Carbon will always want to form 4. Nitrogen has 3 bonds and what else? 1 lone pair, exactly. Oxygen likes to form 2 bonds and how many lone pairs? 2. And the halogens, chlorine, bromine, fluorine, iodine, like to form 1 bond and how many lone pairs? 3, exactly. So these are our building blocks for neutral elements. Now, we can use this formal charge equation and we can come up with an interesting shortcut, right? If formal charge is the group number minus the number of bonds plus the lone pair electrons, we can use this equation to look at the bonding preferences for charged atoms. So in general, when a bond is replaced with a lone pair, the formal charge will decrease by 1. This is commonly used to describe anions. So you'll notice many anion formulas have 1 less hydrogen, and as a result, they end up with a negative charge. When a lone pair is replaced with a bond, the formal charge increases by 1. This is mainly describing the cations. And in cases where if a bond is removed, the formal charge decreases by 1. This last case we won't worry about too much. So let's talk about how these rules actually pan out, as this is something I want you to memorize over the course of the weekend. So what I've done for you is I've generated a series of common bonding motifs. This is how you can draw Lewis structures very quickly for organic molecules. So these are all of our neutral bonding motifs. We've already seen these before, right? Carbon likes to form how many bonds? 4. Nitrogen, how many? 3. Oxygen, 2. Now, applying our formal charge rules, when we have a cation, the bonding preferences change slightly. For cations, carbon forms 1 less bond. For nitrogen cations, following our formal charge rules, you'll generally see a nitrogen with 4 groups attached. I'd encourage you to try out the formal charge calculation for any of these motifs that you're not sure about. All of these are common bonding motifs for each cation and anionic species you'll see as part of larger structures. If you understand common bonding preferences, then it allows you to draw structures incredibly quickly. Additionally, we can look at some double or triple bonded structures. You know, for example, carbon, just because it likes to form 4 bonds doesn't mean they all have to be single bonds, right? Does this carbon still have 4 bonds attached to it? Yes. Does this carbon still have 4 bonds attached to it? Yes. Does this nitrogen still have 3 bonds and a lone pair? Yes. Does this nitrogen still have 3 bonds in a lone pair? Yes. This is how we start to generate common patterns and common connections between atoms that we call functional groups. I would highly encourage you to look over this table and try to calculate the formal charge of any of these species on this list that you're not sure about. With that, we're at the end of today's lecture. I encourage you to look over bonding motifs and practice drawing Lewis structures, as we'll be using those extensively next class session.
And will that be on
Yes.
Wednesday?
Yes.